So imagine looking out the window of a moving train. You're just staring out, and you think you're seeing the world exactly as it is right now. A peaceful, rural landscape rolling by. Green fields, maybe a farmhouse or two. But what if I told you that the landscape you were looking at is actually a ghostly mirage of the past?
Right.
And what if misunderstanding this simple optical illusion might mean some of our most fundamental assumptions about the universe, including Albert Einstein's theory of special relativity, are just completely backwards?
It's an incredibly provocative premise, honestly, because, we rely so heavily on what we see, on the visual information constantly arriving at our eyes, that we rarely stop to question the physical mechanics of that arrival.
Yeah, we just assume it's instantaneous.
Exactly. We assume seeing is believing, but we forget that seeing is a mechanical process, and, it takes time.
And questioning that process is our exact mission for this deep dive. Today, we are opening up a highly detailed, extremely unorthodox source. It's a blog post from a series titled Einstein's Laziness.
Very provocative title.
Yeah, specifically entry number 152. The author uses this meticulous thought experiment involving a train window, imaginary observer characters, and deep dives into coordinate geometry to challenge how theoretical physics handles light.
Right. So the goal of our deep dive today is to unpack this author's highly specific, step-by-step reconstruction of how a localized camera eye actually perceives light.
Okay.
The author is making a really radical claim here. They argue that the famous Lorentz contraction, the established concept in physics that objects actually physically shrink as they approach the speed of light, is just a massive misunderstanding.
Wait, really? That it's totally wrong?
Well, they argue it's not a physical shrinking at all, but rather a simple optical illusion caused by what they call information delay.
Wow. I mean, it's a heavy claim. But before we get totally lost in the weeds of relativity, we definitely need to lay down a crucial disclaimer.
Yes, this is important for you listening. The source material takes a very critical, highly combative stance against established theoretical physics, specifically targeting the foundational work of Albert Einstein and Hendrik Lorentz.
Right.
In this deep dive, we are not taking sides, we aren't endorsing these views, and we aren't validating the complex mathematical formulas the author presents.
Definitely not checking your math today.
No, our goal is strictly impartial. We are here to explore the fascinating mechanical thought experiment the author has built, to understand the argument they're making, and to convey the ideas exactly as they're contained in the original source material.
Basically, we are just the tour guides through this unique intellectual landscape. So let's build the world the author sets up. To start, we have to strip away everything we take for granted and start with a completely blank slate.
Okay, lay it out.
Imagine Earth is an electromagnetic field. Its speed is 0. It is not rotating. It is entirely still. And sitting in this field is our train, also completely still.
Okay, got it. Inside this motionless train, the author places a camera eye. This represents our local observation point. And the primary boundary between this camera eye and the outside world is the train's side window.
The window is key here.
Right. The author defines this window using a strict Cartesian coordinate system. So, picture a graph. The window is a perfectly flat, two-dimensional plane, which they label the y=0 plane.
So the window glass itself is the absolute dividing line between inside and outside.
That's the idea. Outside the window, that rural landscape you imagined, exists in the positive space, where the e-coordinate is greater than 0.
Right.
Inside the train cabin, where the camera eye sits, is the negative space, where y is less than 0. And the window itself is framed as a specific mathematical rectangle, specifically a 40 by 20 or 20 by 20 unit grid.
Wait, if I can just push back for a second on that. Isn't that just standard physics?
So
Well, we abstract things to do the math, right? Like if I'm drawing a map of my neighborhood to show you how to get to the grocery store, I'm not going to draw every single blade of grass or individual pebble on the sidewalk. I draw the lines for the streets and a square for the building.
Sure.
Abstraction is just how we make sense of complex systems without getting overwhelmed,
Your map analogy is actually the perfect way to understand the author's first major philosophical claim. The source argues that this specific abstraction, treating the window simply as a 2D geometric plane in a formula, is exactly where the giants of physics went wrong.
Oh, interesting.
The author claims that Hendrik Lorentz and Albert Einstein treated this mathematical plane as objective space. And by doing so, they supposedly erased the actual physical mechanical process of a localized camera eye actively receiving light.
Erased it. I'm not sure I follow that. I mean, how do you erase the receipt of light?
Think about the history of physics for a second. Isaac Newton believed in absolute space and something called instantaneous action at a distance.
Okay, action at a distance.
This was the idea that gravity instantly affects planets across the void of space, with absolute zero travel time. The author insists that in an electromagnetic world, there is no such thing as instantaneous action. Everything takes time to travel.
Oh, right. Nothing is instant.
Exactly. We must meticulously track the information delay of light traveling from that rural landscape, hitting the window glass, and finally traveling through the cabin to reach the eye.
Got it.
By treating the window as just a geometric plane in a formula, the author claims relativity ignores the actual time it takes for the light to cross that specific threshold and report its data to the observer.
Okay, I think I'm seeing the gap here. It's the difference between a continuous stream of information and just pretending things basically teleport inside the train.
Precisely.
And to track that continuous stream, the author introduces a very specific cast of characters onto the window glass itself, right?
They do, yeah, to visualize the mechanics of this delay. On the exact plane of the window, right on the glass at y=0, the author places a purple camera eye perfectly in the center.
A purple eye. Okay.
Then, flanking that purple eye, on the left and right sides of the glass, are two white dummy dolls. The author calls them the left general and the right general.
I just love this narrative flair. It
Yeah.
helps so much. And then there's one more character deep in the cabins, right?
Yes. Behind the window, further back in the negative space inside the train, is a red camera eye. So we have the glass intercepting the light and the deep cabin actually processing it.
Right.
Now, let's imagine an event. Actually, two events happen perfectly simultaneously in the positive space out in the rural landscape. Let's say two massive flashes of light go off at the exact same time, at the exact same distance from the train.
Okay. So these flashes travel toward the window. And because they happen at the exact same distance and at the exact same time, the light hits the left general and the right general on the glass simultaneously. Boom.
In objective reality, yes, the light strikes the glass at the exact same moment. But here is where the author breaks down the illusion of simultaneity.
How so?
Even if the light hits the left general and the right general at the exact same time, their job isn't done. The physical observer hasn't seen it yet. The generals then have to report this data inward.
And the source says they use blue radio waves to send this report, which, is really just a metaphor for the internal transmission of the light data across the observer's local space.
Exactly. They send these blue radio waves to the purple camera eye sitting in the center of the glass, and they also transmit a report to the red camera eye sitting deeper inside the train cabin.
This totally reminds me of a stadium wave.
A stadium wave?
Yeah, like if two people on absolute opposite ends of a massive football stadium start a wave at the exact same second, the people sitting right in the middle don't see it happen instantly.
Right.
They have to wait for the visual information, the wave of bodies standing up, to physically cross the distance of the stadium.
That is a phenomenal way to picture it. The author's central point is that the report takes time to travel across the local space. And furthermore, look at our setup. The purple eye on the glass receives the report before the red eye deep in the cabin does.
Because it's closer.
Simply because the red eye is physically further away from the glass, yeah. Therefore, an event that is objectively simultaneous out in the landscape is absolutely not simultaneous by the time the localized deep cabin camera eye processes it.
Wow, okay.
The delay in the report fundamentally changes the perception of the event. The author claims this information delay is the missing mechanical reality that relativity completely glossed over.
Okay, so we've established that even when a train is sitting completely still, there is a mechanical delay that basically warps our perception of now. But the whole point of relativity is about things moving, right?
Right, and this is where the author shifts the thought experiment into high gear. The train is no longer sitting at speed zero. The window plane is now moving to the right at a specific extreme velocity. The source uses the value v equals 0.6 c. That means the train is moving at 60% of the speed of light.
Man, if you're listening to this and trying to picture 60% the speed of light, just know it is incomprehensibly fast. So how does moving to the right change those blue radio wave reports from our generals on the window? Let's trace it out.
It changes the geometry of the delay completely. Because the window itself is now moving rapidly to the right, the internal signals are affected.
Okay, how?
Well, the left general is sending a blue radio wave report to the center purple eye, but the center purple eye is moving away from the left general. So the left general signal gets a tailwind. It essentially has to chase the center eye.
Oh, I see.
Conversely, the right general is sending a signal toward the center, but the center purple eye is rushing toward the right general. So that signal faces a headwind.
So because of the movement, the physical distance the internal signals have to travel to arrive at the camera eye fundamentally changes. The left signal travels further, the right signal travels less.
Yes. And the red eye deeper in the cabin. The geometry for its incoming signals becomes incredibly complex, tracing these slanted lines through the cabin as the train moves forward.
That sounds like a math nightmare.
It is. To illustrate just how bizarre this gets at high speeds, the source introduces its most striking visual. Imagine sitting in that moving train and sticking your left arm straight out the window, extending 10 units deep into the outside world.
Okay, so your fingertips are at coordinate y equals 10. Just feeling a 60% speed of light breeze on my fingers. What happens to the arm?
Let's walk through the math the author provides, and let's go slowly. First, let's look at the baseline. When the train was completely still. If the red camera eye inside the train takes a photo of your extended hand at exactly time 0, let's call it 10 equals 0.
Okay.
The light it captures from the tips of your fingers didn't actually leave your fingers at time 0.
Right, because your fingers are 10 units away. The light has to cross that distance.
Exactly. It takes 10 units of time for light to cross 10 units of distance. So the light arriving at the camera at time 0 actually left your fingers at time minus 10, or t equals negative 10.
So even sitting still,
Yeah.
I am photographing the past. My hand as it was 10 moments ago.
Mm-hmm.
I mean, I get that. But what's revolutionary about seeing a delayed hand at a train window? We know light takes time to travel.
Here is the crucial mechanical shift that happens when we apply that velocity of 0.6 c. The author asks us to calculate what the camera sees at time 0 when the train is moving that fast.
Okay.
The light still has to cross those 10 units of distance from the hand to the window, but remember, the camera eye is moving forward the whole time.
Oh, okay. So the light can't just travel in a straight line perpendicular to the window anymore.
Exactly. If the light traveled in a straight line, it would hit the window where the camera used to be and completely miss the camera. For the light from the hand to successfully hit the moving camera eye at time 0, it had to travel on a slanted diagonal path, a hypotenuse.
And geometrically, a hypotenuse is always longer than a straight perpendicular line.
Yes, and because the path is longer, it takes more time for the light to traverse it. When the train is moving at 60% the speed of light, the light arriving at the camera at exactly time 0 actually had to depart from the hand at time minus 12.5.
Wow. Okay, so instead of a 10-unit delay, the movement stretched the delay to 12.5 units because the light had to take a longer diagonal path to catch the moving camera.
But here's the real kicker. Because it took 12.5 units of time, we have to ask, where was the physical hand 12.5 units of time ago?
Well, the hand has been moving forward with the train this whole time.
Right. So the light that arrives at time 0 left the hand when the hand was way further back in space. The author calculates that the light arriving at time 0 left from the physical coordinate x equals negative 7.5.
Wait, let me make sure I'm fully visualizing this.
Go on.
The camera takes a picture at time 0. The actual physical flesh and blood hand at time 0 is right outside the window, directly next to the camera at x equals 0.
Correct.
But the image the camera captures is of the hand when it was way back at x equals negative 7.5.
Yes. The camera captures an image of the hand that is completely disjointed from where the physical hand actually is at that exact moment.
That is just crazy.
The movement, combined with the delayed diagonal path of the light, means you are capturing a ghostly photograph of a past location, while the physical object itself has already moved on.
That is deeply unsettling, to be honest. The image I'm seeing, the visual data my brain is processing, and the actual physical reality of the object are just completely divorced from one another.
Yes, they are.
But if this visual delay creates such a distorted, disjointed image of a hand, wouldn't this optical illusion completely ruin how we measure things in real life?
That is the exact question the author anticipates, and it brings us to their grand synthesis. They explicitly connect this train window analogy to one of the most famous and foundational physics experiments in history, the Michelson-Morley experiment.
Okay, I've heard the name Michelson-Morley. Didn't that have to do with measuring the speed of light back in the late 1800s?
It did, yes.
But how on earth does a ghost arm out a train window connect to a 19th century physics experiment?
To understand the connection, we have to look at the tool Michelson and Morley used. It was a device called an interferometer. Think of it as a highly sensitive light measuring tool.
Okay.
It works by shooting a beam of light at a half-silvered mirror, which splits the beam into two perpendicular paths. These two beams travel out to separate reflecting mirrors, bounce back, and recombine at a receiver.
Got it.
Scientists use this to try and detect the ether, the supposed invisible medium that light traveled through, by measuring if the light beams took different amounts of time to return depending on the Earth's movement.
Okay, so it's a device that splits light, bounces it across distances, and measures exactly when it returns to a central receiver.
Exactly. Now, the author decodes their train metaphor to map perfectly onto the physical mechanics of that interferometer. In this mapping, the train moving through the electromagnetic field is the interferometer moving through space.
Okay.
The camera eye sitting inside the cabin acts as the central receiver, the point where the light is eventually collected and measured, and the tip of your left arm sticking 10 units out the window.
Let me guess. That represents one of the reflecting mirrors, specifically the one positioned perpendicular to the direction of motion.
You got it.
I see the board being set up here. So the light travels out the window, hits the fingertips, which act as the mirror, and bounces back to the camera eye.
Now, here is where the author synthesizes their ultimate, highly controversial conclusion. We just proved that when the train is moving, the light returning from the arm takes a longer diagonal path, severely delaying the image and making the arm appear further back in space than it actually is. The author argues that the same mechanical delay happens inside the interferometer. But how does this explain Lorentz contraction?
Right, because Lorentz contraction is the accepted physics principle that as an object approaches the speed of light, it literally physically compresses in the direction it is moving. How does a delayed image equal a physically shrunken object?
It comes down to how a moving camera receives light from the front of an object versus the back of an object. Imagine a long train car zooming past our localized camera eye.
Okay.
The light from the front nose of the train has to travel a certain distance to hit the camera. But as the train moves forward, the back tail of the train is rushing toward the location where the light from the nose was emitted.
Oh, I see where this is going.
Because of this motion, the light from the back of the train takes less time to reach the camera than the light from the front. The visual information from the back catches up faster.
Wow.
So when the camera processes the complete image of the train, the visual data is compressed. The back appears closer to the front than it physically is.
That is wild.
The author claims that if you calculate the mathematical value of this purely visual optical squishing caused by information delay, it perfectly matches the mathematical formula for Lorentz contraction.
Wait, let me stop you right there. Are you saying the author is claiming that objects don't actually physically shrink at all? That the math works out just because it's an optical illusion caused by the lag of light?
The source argues exactly that. They claim that Lorentz, and subsequently Einstein, took an optical illusion, a measurement error caused strictly by the mechanics of information delay, and mistakenly assumed that the physical universe itself, the actual fabric of space, was contracting.
That is an incredibly bold claim. They're basically saying the greatest minds in physics fell for a mirage because they didn't mechanically account for the travel time of the light arriving at the observer.
The author views their own work as a triumph of engineering over theoretical physics.
Engineering, huh?
Yes. From an engineering standpoint, you cannot abstract the process. You have to track every physical input and output. You have to mechanically account for the delay of the signal across the geometry of space. The author is demanding that we separate the map from the territory.
The map being the visual image the camera eye receives.
Yes. And the territory being the actual objective physical location of the objects in space at that exact moment. The author believes relativity confuses the delayed map for the physical territory.
Okay.
By meticulously tracking the slanted diagonal paths of light like an engineer, rather than abstracting the window away as a simple 2D plane like a theorist, the author believes the need for a physically shrinking universe simply vanishes. It is replaced by a universe where information just takes a really, really long time to cross diagonal paths when things are moving fast.
Man, what a wild intellectual ride this has been today. Let's recap how we got here. We started with a very grounding, everyday image, just looking out a train window at a rural landscape.
Right.
Then we placed some imaginary generals on the glass to track exactly when light hits the barrier and how long it takes to report that data into the cabin. We stuck an arm out into a 60% speed of light wind, mapped out the geometry of a hypotenuse to realize we were taking photographs of ghosts from past coordinates.
Yes, exactly.
And somehow ended up mapping that entirely onto the Michelson-Morley experiment to reevaluate the foundational proofs of special relativity, all through the lens of pure mechanical information delay.
It's a testament to how a single, rigorously applied thought experiment, just following the geometry step by step, can attempt to dismantle a century of accepted theory. And whether you agree with the author's controversial math or stand firmly with Einstein, it forces you to interrogate how much you trust the visual information arriving at your own camera eyes. Which leaves you with something pretty profound to mull over.
Lay it on us.
If the author's thought experiment holds true, if there is a permanent, inescapable mechanical delay between when something happens and when our local camera eye perceives it due to the sheer travel time of light, then we have never actually experienced the present moment of anything outside our own bodies.
Oh, wow.
Everything you see, everything you interact with, even the device you are listening to right now, is just a delayed ghost of the past finally arriving at your personal coordinate. Are we all just navigating a universe of outdated information, forever chasing a present we can never actually touch?
And on that note, next time you're looking out a train window, just remember, the landscape you're admiring might not actually be there anymore.